Good afternoon, everyone. Welcome to 12th week of discussion session of the course Plates and Cells offered by NPTEL. The course instructor of this course is Professor Sudip Talakdar, and I am your teaching assistant. I am Asif Raza. I am a PhD scholar from Department of Civil Engineering, ISC Bangalore. So today we'll be discussing questions relevant to assignment number 11. So without any delay, let's start. Let's start a session. Okay, so the first question is first let me do this. Okay, the first question is the equilibrium equation of forces in radial direction of cylindrical shell roof with the assumption of membrane theory is. First option is an algebraic equation, second is a second order non-homogeneous ordinary differential equation, third is the second order non-homogeneous ordinary differential equation with variable coefficient, and fourth option is fourth order polynomial equation. So the equation, the equilibrium equation of forces in radial direction is n theta plus z are equal to 0. So this equation is an algebraic equation, so the correct option would be option A, an algebraic equation. So let's move on to the next question. The correct name of the following parts of the cylindrical shell roof as shown in figure. Okay, so you can see the first is a curve on which our generator travels to generate the shell. So this curve is called as a directrix, and it can be circular, catenary, cubical. Yeah, okay. The second one is a generator. Third one is a traverse on which a shell roof rests, and fourth one is my edge beam. So the correct option would be option B. Okay. Okay. Third question is in analysis of a simply supported cylindrical shell roof subjected to uniform vertical load using membrane theory, the origin is selected at the crown of the midspan. In such case, boundary condition at x equal to 0 is nx theta equal to 0. The imposition of such condition is justified because the options are the shell is thin structure, the shell is simply supported, the problem is symmetric, and the last option is there is no hole in the cell. So if you see the previous diagram, the question is asking about this curve at x equal to 0 and x theta is equal to 0, and this is possible as the problem is symmetric. So correct answer is option C. Okay. Next question. A circular cylindrical shell of reinforced concrete with R equal to 6 meter is subjected to shelf weight. The thickness of the cell is 80 mm. The density of concrete is 24 kilonewton per meter cube. The magnitude of n theta in kilonewton per meter at an angle theta equal to 30 degree is. So we are given with R equal to 6 meter, thickness is 80 mm, it should be equal to 0.08 meter, and density of the concrete is given as 24 kilonewton per meter cube, theta is given as 30 degree. Okay, so the with this dead load intensity would be gamma times h, and that is 24 into 0.08, and that will give me 24, 8 for 32, it is 16, 1.92 kilonewton per meter square. Okay. Now, uh, uh, for a general cylindrical shell, it is denoted by this: r theta is equal to r naught cos n theta, and as we are given a circular cylindrical shell, so for circular cylindrical shell, we have r naught is equal to r and n is equal to 0. Okay, so this will give me r naught is equal to 6. Okay, then which is equal to r of theta, and this z is equal to omega cos theta. So okay, now we have r we need to find n theta, and we have equilibrium equation with respect to radial direction as n theta plus z are equal to 0. This will give me n theta is equal to minus zr, and z is wg cos theta, and r is equal to r naught. So finally we can substitute 1.2 cos 30 times 6. So this will be equal to 1.92 This will give me 9.9766 kilonewton per meter. So the magnitude of n theta would be equal to 9.9766 kilonewton per meter, and if you round it off, it will be equal to 9.98 kilonewton per meter. So the correct option is option D, 9.98 kilonewton per meter. So now let's move on to the next question. Fifth question is: a radius of curvature of a cylindrical shell can be expressed as r equal to r naught cos to the power n theta, in which r naught is radius of curvature at the crown. The value of n in case of parabolic directrix is. So as you have all studied in lecture 2, module 11, so we can just write it everything. So for circular directrix, we have r naught is equal to r and n is equal to 0. Okay, then for directrix, for cycloidal, we have r naught is equal to minus 4 and n is equal to 1. For catenary directrix, we have r naught is equal to a and n is equal to minus 2, and for parabolic directrix, we have r naught is equal to 2a and n is equal to minus 3. So according to the question, we have it's asking about parabolic directrix. The value of n is equal to minus 3. So my correct option would be option A, minus 3. So now let's move on to the next question. A circular cylindrical shell is to be analyzed using membrane theory. The dead load and snow load are expressed as Fourier series. Only first term of the Fourier series is taken from the analysis. If the dead load intensity is 1.2 kN per meter square and snow load intensity is 1.8 kN per meter square, the ratio of maximum value of longitudinal stress in case of snow load to that in case of self weight is. So you can refer to the module 11 lecture 3. So we are given with dead load intensity Q is equal to 1.2 kilonewton per meter square and no load intensity uh, 1.8 kilonewton per meter square. So maximum longitudinal stress due to snow load is given by 12 p L square by R pi cube cos pi x by L times cos 2 theta c minus theta, and this will be maximum uh, uh, maximum at x equal to 0 and theta is equal to theta c. So nx maximum for snow load is 12 p L square R pi cube. Okay, so this is my file. Now nx due to dead load is 8 q L square R pi cube cos pi x by L cos theta c minus theta, and this will be maximum at x equal to 0 and theta is equal to theta c. So this will give me nx max for dead load is equal to 8q L square by R pi cube. So this is 2. When we take the ratio of 1:2, will be having 12p upon 8 cube, and that is 12p is 1.8, 8 q is 1.2. It will be this cancel out, will be left with 18 upon 8, and this can be written as 2 4 is 8 to 9, 9:4. So my answer would be 9:4. So correct option is option D, 9:4. Now let's move on to the next question. Okay, a given with a circular cylindrical shell of span 24 meter, chord width 10 meter, central rise 2.5 meter is subjected to self weight. It is required to determine the membrane stress Nx at 6 meter from the center of the span and at theta is equal to 45 degree. When the shell is simply supported on the traverse, the angle theta is measured from the ground. The shell is made of reinforced concrete of thickness 70 mm. Assume specific weight of concrete as 24 kN per meter cube. We need to find the value of nx in kilonewton per meter, correct up to 2 decimal places. So let's sum it up. What we are given with, a span of 24 meter, chord width we can write as 10 meter, thickness is given as 70 mm, so it is 0.07, or just write thickness as t, 0.07 meter. Central rise I am writing it as h, and it is equal to 2.5 meters, and is subjected to self weight. Okay, so and density of concrete is 24 kilonewton per meter cube. So with this, okay, so let's draw the diagram. We have a circular cylindrical shell. We have a circular cylindrical shell. Now we have a chord width as 10 meter, that rise as h is equal to 2.5, or I'll just write h here, L by 2, and this would be my radius, so this would be equal to r minus h. Okay, so using Pythagoras theorem, we will be having r square is equal to r minus h whole square plus L by 2 whole square. Substituting the values, will get r minus h is 2.5 square plus 10 by 2 square, that will have r square equal to r square plus 2.5 square plus minus 5r plus 5 square. So this will give me r as 5 square plus 2.5 square by 5, and 5 square plus 2.5 square divided by 5. This will be equal to 6.25 meter. Okay, now also we have dead load intensity as gamma c times thickness, just t, and that is equal to 24 into 0.07, and that would be 10^28 and 1.68. Okay, so 1.68 kilonewton per meter square, that is my self weight. Now we need to find the value of nx. So for general cylindrical shell, it is given as r0 cos n theta, and as we have circular cylindrical shell, r0 is equal to r and n is equal to 0. Okay, r0 is equal to r and n is equal to 0. We need to find nx. So generally nx is given by the relation -n plus 2 by 2 Z L by 2 whole square minus x square 1 upon r theta, and we have z is equal to wg cos theta. So this would be equal to 1.68 cos 30. Okay, no, sorry, 45. Theta is 45 degree. So substitute it. Nx at x equal to 6 and theta is equal to 45 degree. We'll be having minus 2 by 2, 1.68 cos 45. L is 24 by 2 square minus x is 6 square 1 upon r theta, and r is minus 6.25. So let's solve this. 12 square minus 36 6.25 into 1.68 into 45 cos, it's equal to minus 20.527 kilonewton per meter. We need to rounding it off to 2 decimal places. We can write minus 20.53 kilonewton per meter, and this is my answer. Okay. Yeah. Now let's move on to the next question. So we are given with a cylindrical shell roof with cycloidal directrix of span L equal to 20 meter. Radius at the crown is 2 meter. Radius at the crown R naught is equal to 2 meter. Is subjected to self weight 1 kN per meter square. The magnitude of circumferential stress n theta in kilonewton per meter, rounded off to second decimal places at theta equal to 45 degree is. So we're given with cycloidal directrix. So with r naught is equal to 2 meter and n would be equal to minus n would be equal to 1 in this case, and span is given as 20 meter and self weight is 1 kilonewton per meter square. We need to find out theta equal to 45 degree value of n. Okay, so let's do this. The equilibrium equation with us for in radial direction is equal to what? N theta plus z r equal to 0. Okay, so n theta will be equal to minus z r, right? And we have z is equal to g cos theta. Okay, so z would be equal to wg cos theta, and r is equal to r naught cos n theta, and n is equal to 1 for this case, so r naught cos theta would be my r. So substitute this here, r naught cos theta. So finally the magnitude of n theta can be written as wg cos theta, wg times r cos square theta. Okay, so substituting the values and theta equal to 45 degree, will be having 1 sin r is equal to 2 and cos square 45 degree. So cos 45 is 1 upon root 2, and that would be equal to 1 to 1 by root 2 whole square. So this will give me 2 by 2 and this will give me 1. So and magnitude of n theta at theta equal to 45 degree is 1 kilonewton per meter. So this is my answer. Now let's move on to the last question of today's session. Referring question 8, if the shell is provided with H-beams, the magnitude of the axial force in the H-beam in kilonewton rounded off to the nearest integer at a distance x equal to 5 meters from the midspan is. Okay, so let's write the values again first. So we have the cycloidal directrix with r naught is equal to 2 and n would be equal to 1. So r of theta r naught cos n theta would be equal to 2 cos theta. We are given with the span as 20 meter, that weight as 1 kilonewton per meter square. Okay, so we need to find the axial force in the H-beam. So if you see in the lecture module 11, okay, so refer lecture module 11 lecture 2. So the magnitude of the axial force. So first, axial force can be found out by taking integration from minus x to L by 2 with nx theta at theta equal to theta c, that is at the crown, and integrating with respect to x, and for the H beam theta c. Okay, so let's write it. So it will be minus x is from 5 to L is 20 by 2, and x theta in general is given by minus n plus 2 wg x sin theta and theta at c or dx, and we have theta c is equal to pi by 2 for the H beam. So and n is equal to 1, so we can simplify this by taking 5 to 10, minus minus cancel out, n is equal to 1, so this would be equal to 3 wg x sin theta sin pi by 2 dx, and this would be equal to 3 wg 5 by 10 x dx, and this will be equal to wg is 1, x would be on integration will have from x 5 to 10, and this would equal to 3 by 2, 10 square minus 5 square, and 100 minus 25. This would be 3 into 75 by 2, and this would be equal to 75 to 3 by 2. This will be equal to 112.5 kilonewton. So the magnitude of the axial force in the H beam in kilonewton would be is 100. Rounding it off to the nearest integer would be equal to 112 kilonewton. Okay, that's it. Yeah, so this concludes today's session. If anybody has doubt in this, you can just post it in the discussion forum, and I'll try to answer questions as soon as possible. And by next week, I'll try to uh, post the questions relevant to assignment 12. You can have a look so that it will be helpful for you in the exam, and you can do so. Okay, that's all for today. Have a nice day. Bye.